Hey Chemistry Honor students, this is Ms. Kato. This is your first podcast on Unit 3 on thermodynamics, and this podcast focuses on the subject of calorimeter or calorimetry. This covers all of chapter 17.1 and some of 17.2. I am not going to include in this unit pages 514 to 517, so you are not responsible for these particular pages in this unit. Let's establish what a calorimetry is. Calorimetry is a study of heat flow. So we are going to measure the amount of heat that goes into or out of a system for a chemical or a physical process. We're going to talk about the chemical and physical processes in the second podcast. So we know that a thermometer measures temperature. We know barometers measure pressure. We know meters measure distance. A calorimeter is a device used to measure the absorption or the release of heat. And I put a Q right here because Q is now going to represent heat. So when I say T, it's always going to be temperature. Like I used T before in the gas unit. When I used P before, we were talking about pressure. And now when we say Q, Q is always going to represent the amount of energy or the amount of heat that is either released or absorbed by the system. There are two kinds of calorimeters. There is the constant pressure calorimeter and there's the constant volume calorimeters. These two calorimeters I will talk about more in just a little bit with pictures, so hold on tight for me. But before we go on to that, we need to establish the differences between heat and temperature. We talked about how heat and temperature are different in class, but just to remind you that thermometers measure temperature, which is the average speed of the particles, and we will measure that in Celsius. In Unit 2 in gases, we measured all temperature in Kelvin because the Kelvin scale was directly proportional to the average kinetic energy of the particles. But in this unit, we're not so much necessarily the average speed of the particles. We're talking about the just the temperature, and we're going to talk about it in terms of Celsius. So temperature in this unit is going to be in Celsius. Calorimeters measure heat or the energy, again Q, in either joules or calories. We're not going to use so much the big C calorie, but I may ask you for, you should be able to know, or you should be able to convert big C calories to little c calories. Remember that they are not the same. 1 big C calorie equals 1,000 little c calories, and 1 little c calorie equals 4.18 joules. So if I talk about 1 little c calorie and 1 joule, which one is bigger? I'm going to give you a second to think about it, and you are correct. 1 calorie is bigger than 1 joule. So the heat flow is based on the law of conservation of energy, which states that energy cannot be destroyed or cannot be created. So it has to be that heat only transfers from one thing to another. So in other words, heat release always equals the amount of heat absorbed. So we don't gain any more than what was released, and we don't absorb more than that was the amount of heat that was released. Heat flows always from the warmer to the cooler, so that is not going to happen. Okay? And system is what we are focused on. The surrounding is what surrounds the system, and the universe is something outside of it. So if I were to draw a picture, whatever I am interested in will be the system. Whatever surrounding the system is called the surrounding. And everything outside of that is the universe. So there are different kinds of systems. Mostly we're going to be talking about the open system here, but we'll talk just really a little bit about the closed system and not very much at all on the isolated system, but let me just give you some vocabulary here. Open system is when both matter and energy are exchanged with the surroundings. The system exchanges both matter and energy. In a closed system, only the energy is transferred between the system and the surrounding, and in an isolated system, neither energy nor matter is exchanged with the surrounding. So to give you an example, I'm going to talk about one kind of a calorimeter. And this is a kind of a calorimeter that we use in class for the WCI3. As you can see, this is just a foam cup, and it is double layered so that it's insulated better, and it has water in it, and it has a little bit of lid. This lid is a styrofoam cover. It is not an airtight lid. In other words, air can go in and air can go out. Sorry, I drew that the wrong way. So air goes in and out. Air goes in and out. And air, as you know from Unit 2, air is made out of particles, and particles are matter. And so matter it can be exchanged from in and out. So we have an exchange of matter. And also, being that the atmospheric pressure is not going to change dramatically, we're gonna, sorry, let me say that again. The atmospheric pressure is not going to change dramatically within one experiment. So let's say at sea level we have 1 atmospheric pressure, and the atmospheric pressure is going to remain the same within an experiment. Considering that this is not an airtight system, and air can go in and out, it's going to the pressure is going to equalize so that the outside pressure is the same as the inside pressure. And as long as the outside atmospheric pressure is not going to change, the inside pressure is going to be the same as the outside, which is in this case 1 atmospheric pressure. So in this case, the air is being transferred in and out, as well as heat can go in and out also. Heat can go in and out. And so this is an example of an open system. Okay. When we are in an open system, which is also the constant pressure system, Q, which is, as I said before, heat, is also equal to enthalpy, a special kind of heat, which is only qualified under the constant pressure environment. And this enthalpy has a symbol of delta H, and for the purposes of this chapter, Q is going to equal delta H because we are always going to do our experiment under the constant pressure condition, which is going to be an open system. Foam cups, there are 2 cups so that it has better insulation, and this is an example of an open system. A bomb calorimeter is a constant volume calorimeter, and in this constant volume calorimeter, Q does not equal delta H because we don't have a constant volume condition. Let me tell you why we don't have a constant pressure. Sorry, I said volume, but we don't have a constant pressure environment, and let me tell you why we don't. So this is a bomb calorimeter. that is often used to measure the energy in food content. They put a little bit of food here, and this is an electrical lead that is connected to the food. And once there's an ignition in the wires, it makes that the food inside burn. And as the food burns, it gets warmer in the smaller container. And as the smaller container becomes warm, the outside of the smaller container water becomes warmer, and they measure the temperature of the temperature difference or temperature rise of the water outside of the smaller container. So here's my thermometer. It is a steel bomb, meaning that it is a closed steel container, and so matter cannot go in and out of this smaller container. And because matter cannot, but the heat can, this is called a closed system. An example of an isolated system is kind of like a thermos. So let's say that you have a thermos bottle, and when it is a double container, where inside or between the smaller container and the larger container is a vacuum. And depending on how great this thermos is, the vacuum is better. And if you touch the outside of, this is my hand, outside of this thermos, you're going to not feel that the thermos outside is very hot. However, if you open the lid, it's very, very hot. So in other words, heat is not able to get out. Heat cannot move out. Nor can matter come in and out. So this will be considered an isolated system. Let's talk about some of the processes of heat flow. The two kinds are the exothermic and the endothermic, and we talked about this a little bit in class, in that the exothermic process is when the heat flows out of the system and into the surrounding. Okay, so once again, here's my system, here's my surrounding, and the system loses the heat to the outside, and this is called the exothermic process. Okay, versus an endothermic process, the heat flows into the system from the surrounding. So again, energy is not created or destroyed, but it is just flowing from the surrounding to the system. And so this would be considered an endothermic process. Okay, if I were to give a symbol to the endothermic and exothermic heat, I'm going to let you know that Q and H is always going to be negative when the system is losing the heat. So if I have a negative value for the Q or a negative value for the delta H, you would know immediately that this is an exothermic process. And if you have a positive Q or a positive delta H value, you immediately know that the system is gaining the heat, and so it would be an endothermic process. And I cannot write as I talk. Endothermic process. Okay? Either way, heat is not created or destroyed. It is equal to each other, except that now I'm going to add a symbol of a negative value in front of the heat that is lost.